Good day, everyone. In this video, we will be looking at section 3.7, which is on the Poisson distribution. By the end of this video, which has been divided into three sections, part 1a, part 1b, and part 1c, by the end of the entire video, you should be able to recognize and know the PMF of a Poisson distribution, and recognize that the Poisson probability distribution is a limit of the binomial distribution. You should also be able to indicate the relationship between parameters of the Poisson and the parameters of the binomial distribution, as well as show that the Poisson distribution and its PMF are valid PMF, and it is a probability distribution. And then you should also be able to identify a random variable as a Poisson random variable if given a practical scenario. You should also be able to calculate probabilities using the PMF and also using the Poisson probability tables. And you should also be able to derive the expression of the mean of the Poisson distribution. Now, the Poisson distribution was named after a French mathematician and physicist, Simeon Poisson, and he developed this distribution, which is named after him, in 1837. And the first application of this distribution was on a description of the number of deaths by horse kicking in the army. So he was a mathematician as well as a physicist, and he worked on various things such as statistics, complex analysis, partial differential equations, as well as analytical mechanics. Right, so he described the Poisson probability distribution as follows. So the definition says a random variable x is said to have a Poisson distribution with parameter lambda, where lambda must be positive, so lambda must be greater than 0, if the PMF of the random variable x is given as that expression there. So the PMF px with parameter lambda, so lambda is a parameter, we need this value to calculate probabilities, all right? So the PMF is defined by px with parameter lambda. This is the probability that x is equal to some particular possible value. And so the PMF is equal to e to the power minus lambda times lambda to the power x, all divided by x factorial, for x equal to 0, 1, 2, and so on. So for the Poisson distribution, they tell us that the possible values of a random variable x is 0, 1, 2, 3, and so on. So the minimum value for Poisson random variable is 0. All right. Okay, so how can we show that this PMF is a valid PMF? Well, there are two conditions. Firstly, we can show that the PMF is greater or equal to 0 for all possible values of x. And so if you start with x equal to 0, then let me write it at small letter p. So it should look like a small letter p for PMF. So P0, which is the probability that x is equal to 0, that is equal to e to the power minus lambda times lambda to the power 0, all divided by 0 factorial. And that is just equal to e to the power minus lambda, and that is 1 divided by e to the power lambda. That is greater than 0. Okay, the exponential function or e to the power lambda, where lambda is a positive value, we know that this value here is a positive value, and so the final answer will be positive, all right? And then P1 is equal to the probability that x is equal to 1, that is e to the power minus lambda times lambda to the power 1 divided by 1 factorial. that is just equal to lambda divided by e to the power lambda. And so for lambda that is greater than 0, we see also that P1 is greater than 0. And so if you continue and have a look at x equal to 2, 3, 4, and so on, then you'll see that Px will be positive, greater or equal to 0 for all values of x. All right, so we have done the first requirement for valid PMF. The second requirement for valid PMF is that the sum of all the probabilities for all possible values of x must be equal to 1. That is what we need to prove. All right, so we will start with writing out the summation. So we're summing e to the power to the negative lambda times lambda to the power x divided by x factorial, and we're summing from x equal to 0 to infinity. Why? Because the definition says x is equal to 0, 1, 2, 3, 4, 5, and so on. All right. Now, what can we do next? So we can take out the constant e to the power minus lambda and put it right in front of the summation sign, right? Since we're summing from x equal to 0 to infinity. Right, so since e to the power minus lambda is a constant, we can then put it in front of the summation sign, and so we will have e to the power minus lambda times the summation of lambda to the power x divided by x factorial, where x goes from 0 to infinity. Okay? Alright, so in mathematics we have a result that says the series sum of I when I goes from 0 to infinity of u to the power I divided by I factorial, that this series here is equal to e to the power u. Alright, so what do we have here that we can use to simplify the summation? Right, so we have sum of x equal to 0 to infinity of lambda to the power x divided by x factorial. Alright, so do we see similarities here? So we have I there, we have x there. I goes from 0 to infinity, x goes from 0 to infinity. We have that the summation of u to the power I, there we have lambda to the power x. And then here we have divided by I factorial, there we have divided by x factorial. Okay, so we see that this summation is similar to that summation there, right? So if this summation here is equal to e to the power u, then it means that this summation here is equal to e to the power, what is it? Lambda, right? So we see that we have u there, and so it's e to the power u. We have lambda there, and then it's e to the power lambda. Alright, so using this result, we have e to the power minus lambda times e to the power lambda or using this result of summation x equal to 0 to infinity of lambda x factorial is equal to e lambda, and so this is then equal to 1. So we see that the summation of the probabilities is equal to 1. So we have shown then that the PMF of a Poisson distribution is indeed a valid PMF. Right, so it's a valid probability distribution. Alright, so where is this distribution applied? It says there that a Poisson random variable denotes the number of successes on average per unit measurement. Alright, so the main aim of the Poisson distribution is to calculate the probability of a given number of events that would occur in a fixed interval of time or space, right? If these events occur with a known constant mean rate, and if these events are independent of each other, all right? So we want to calculate the probability of observing a certain number of events or number of successes that can happen within a fixed time, interval of time or space, right? It could be time, it could be space, it could be certain events that happen within a period, a certain period. And so we want to calculate the probability of observing these number of successes per unit of measurement, given some known average or mean rate. Okay, so let us look at a couple of examples. So suppose the number of power outages in Tshwane on average is 4 per month. All right, so it's like 1 per week, once a week. So determine the probability that there will be more than 4 outages in any given month. So here we're looking, the period here is per month. So we're looking at 30 or 31 days or a month, right? And on average, we know that they're telling us that there are 4 per month, but we know that it's more in current times, right? Okay, so suppose that we're just looking at an example where on average we have 4 outages per month. Now, we will use the Poisson distribution to calculate the probability of observing more than 4 outages in a given period or a given interval of time. In this case, the time or space that we're looking at, it's a month, right? Okay, so the second example says, suppose that on average 6 births occur at Steve Biko Hospital per day. So in 24 hours, we have on average 6 births. Okay, obviously some days will have fewer births and some days will have more. Then what is the probability that during New Year's Day, Steve Biko Hospital assists in the birth of only 4 babies? Okay, so now we want to calculate the probability of only observing 4 successes or 4 births, given that on average we know that there's 6 births per day, right? So the Poisson distribution is applicable here because it can help us calculate the probability of observing 4 successes in 24 hours, given that on average there are 6 births in 24 hours. Right, so the third example says approximately 0.56 meteorites weighing 10 grams or more strike the earth every 1 hour on average. Okay, so this is information that we can assume that on average we have 0.56 meteorites weighing 10 grams that strike earth every 24 hours. Now we will use the Poisson probability distribution to calculate the probability that no such meteorites will fall to Earth in any given hour. If it is assumed that on average we have 0.56 meteorites. All right? And then the last example says, suppose that trees in a forest are more or less evenly distributed with an average of 291 trees per hectare. Again, the word on average, with an average of 291 trees per hectare. So the fixed space here, the fixed space that we're looking at here, it's per hectare, right? Then we'll use the probability distribution to calculate the probability that a randomly chosen hectare in the forest has at least 324 trees. Right, so if on average we know that there's supposed to be 291 trees, what's the probability that a randomly chosen hectare in the forest has at least 324 trees? So we'll use the Poisson distribution to calculate these probabilities of somewhat rare events. In the textbook they say rare events, but if you know that on average certain events would occur at a given time period or space, and so we want to calculate the probability of observing more or less number of successes at those specific units of measurements, or per month, or per day, or per hour, or per minute, or per hectare. All right, so example 3.47 says, let X denote the number of creatures of a particular type captured in a trap during a given time period. Okay, during a given time period. Suppose that X has a Poisson distribution with parameter lambda equal to 4.5. Yes, so we see that lambda is positive. That is one of the criterias under the definition, that lambda must be positive. So on average traps, suppose that X, let me read it again. Suppose that X has a Poisson distribution with lambda equal to 4.5. So on average traps will contain 4.5 creatures. On average, each trap will contain, or assume will contain 4.5 creatures. Right, so now we need to calculate the found probabilities. So what is the probability that a trap will contain exactly 2 creatures? Alright, so we're told here that a random variable X follows a Poisson distribution with parameter lambda equal to 4.5. So I will write it as X, and then that wave, meaning distributed as or follows the Poisson distribution with parameter 4.5. So the Poisson distribution only has one parameter. Okay? And so now we want to calculate the probability that a trap will contain exactly 2 creatures, when on average a trap will contain 4.5 creatures. Okay, so on average we expect or assume that a trap will contain 4.5 creatures, but we want to calculate the probability of this rare event, that a trap will contain only 2 creatures. Okay, so we're calculating here P2, which is the probability that X is equal to 2. And by definition, if we use then our formula, it says that a PMF is equal to e to the power minus lambda times lambda to the power x divided by x factorial. And so this is equal to e to the power minus 4.5 times 4.5 to the power 2, all divided by 2 factorial. Right? So the formula of the PMF, it's given as that. Now this is equal to 0.1125. So we see that there's a 0.1125 or 0.1 probability that a trap will contain exactly 2 creatures. It's a relatively low probability, but it is possible, right? So 11% chance that a trap will contain exactly 2 creatures. Now, what is the probability that a trap will contain at least 1 creature? So now we're calculating probability that X is greater or equal to 1. So at least 1. And so this can also be calculated as 1 minus the probability of X less than equal to 0, right? Everything on the left-hand side of 1. So remember, by definition, they said that this PMF is equal to e to the power minus lambda times lambda to the power x divided by x factorial for x equal to 0, 1, 2, 3, and so on. Alright, so by definition, they tell us that x goes from 0. Alright, so which possible values of x fit this criteria here of x being less than or equal to 0? It's just x equal to 0, right? You agree, right? Yes. Okay, so we have equal to 1 minus the probability of x equal to 0. Now this is equal to 1 minus e to the power minus lambda. Lambda is equal to 4.5, right? So it's negative 4.5 here times 4.5 to the power 0, all divided by 0 factorial. And so this is equal to 0.9889. So there's a 98%, almost 99% chance that a trap will contain at least one creature. There will be a creature in there, all right? Okay. So this is the end of section 3.7, part 1a. In the second part of this video, we will look at two things. Firstly, it's the Poisson distribution as a limit of the binomial distribution, provided that the number of trials n is greater than 50 and the probability of a success is less than 0.5. And then secondly, we will look at the expected value and the variance of a Poisson random variable with parameter lambda. Okay, so we'll look at two things: the Poisson distribution as a limit of the binomial, as well as the expected value and variance of a Poisson random variable. The proposition says, suppose that in the binomial PMF, we let n tend to infinity, so n is some large value, and we let p tend to 0, where p is a small probability value, in such a way that n times p would approach some value lambda that is greater than 0. If that is the case, so if these two things happen, n approaches infinity and p approaches 0, then the PMF of the binomial will approximately tend to the PMF of the Poisson distribution. It is interesting that Simeon Poisson discovered his distribution by this approach in the 1800s as a limit of the binomial experiment. According to the proposition, in any binomial experiment for which n is large and p is small, then the PMF of the binomial distribution will approximately be equal to the PMF of the Poisson distribution, where lambda is equal to n times p. As a rule of thumb, we will say that this approximation can safely be applied if n is greater than 50 and p is less than 0.5, and so n times p will be less than 5. Remember, in the first part of the video, we said that the Poisson random variable in a way denotes a rare event, right? So if, for example, on average, there are 4 outages, power outages in a month, then the Poisson distribution will help us to calculate the probability of observing 10 outages in a month. So the probability of a success, in a way, of this rare event, or the probability of having this rare event, does make sense that it would be some small value. It does make sense that we would have this criteria, that probability of success, of observing those number of successes for a given time period, would be a small probability, or p would be less than 0.5. All right, so this criteria of n greater than 50 and p less than 0.5 does make sense in the context of a Poisson distribution. All right. So again, we said that if n is greater than 50 and p is less than 0.5, which means that n times p is less than 5, then we can safely apply this approximation, meaning you can use the PMF of the Poisson to calculate the probabilities of a binomial random variable, all right? Or in the case when n is greater than 50 and p is less than 0.5, you can use the binomial PMF to approximate probabilities of a Poisson random variable. This is what it means. All right, so let us compare the two types of random variable, the binomial and Poisson. Firstly, with the binomial, we know that we have n fixed trials, meaning before we even do the experiment, we know that we have to repeat the experiment n number of times. While with the Poisson, the number of trials are not really fixed, but it could be some large value or n could tend to infinity. For the binomial random variable, we know that we have a dichotomous outcome for each trial or every time we repeat the experiment. The same goes with the Poisson. We have dichotomous outcome, meaning every time we repeat the experiment, you either have success or failure, or true or false, or yes or no. Then for a binomial random variable, our random variable x is denoted as the number of successes among the n trials. Okay, so it's among the fixed n trials, while with the Poisson random variable x denotes the number of successes within a given period of time, given time or space. All right, with a binomial random variable, the probability of a success p is constant, meaning every time you repeat the experiment, the probability of observing a success will be p for all trials. So every time you repeat the experiment. With the Poisson distribution or Poisson random variable, the probability of observing a success is equal to p. We assume that it's also constant, but it would be small, since we have that assumption that a Poisson random variable in a way denotes some rare event. And then lastly, the expected value of a binomial random variable is equal to n times p, while with the Poisson random variable, the expected value is equal to lambda. Now, example 3.48 says, if a publisher of a non-technical, let me do this. A publisher of non-technical books takes great pains to ensure that its books are free of typographical errors, so that the probability of any given page containing at least one such error is 0.05, and errors are independent from page to page. What is the probability then that one of its 400-page novels will contain exactly one page with errors? Or what is the probability that at most 3 pages will contain errors? All right, so here we are given the following. So we are given the following. So we are told that the probability of observing an error on one page is 0.005. All right, and we're told that the errors are independent from page to page, meaning if there's an error on one page, it doesn't mean that the rest of the following pages will contain errors as well, right? Errors are independent. We have a fixed number of pages for a novel. So we have 400-page novel, all right? So that is what they tell us. And so we in a way, for each page, we could count the number of errors. Or we could say, yes, there's an error, or no, there's no error. Yes, there's an error, or no, there's an error. So for each page, there's a dichotomous outcome. Yes, there's an error, or no, there's no error. All right, so we could see that this type of experiment that we're looking at can be described as a binomial experiment. So if I then, let's say, define my random variable x as the number of pages that contain an error in a 400-page novel. So if I define my random variable x as that, the number of pages that have errors in a 400-page novel, then a random variable x can be denoted as a binomial random variable, which follows. So that wave like or tugle symbol means distributed as, or follows the distribution of the binomial distribution with parameters n and p, where n is equal to 400 and p is equal to 0.05. All right. So firstly, before we calculate the probability that one of its 400 pages will contain exactly where one page will contain errors, let us look at the expected value of errors per page, right? So what is the expected value or the expected number of errors per page? This is equal to the number of pages in this novel, which is 400 pages, multiplied by the probability of an error. Probability of an error is 0.05. And so that is equal to 2. What does this mean? It means that on average, we can expect 2 errors per page. Remember the first part of the video, we looked at some examples where you had those keywords on average and then per something. So we see here that the unit that we're looking at, or the space that we're looking at, is a page, right? So per page, we're expecting 2 errors, or on average, there are 2 errors per page. And so the Poisson distribution can then help us calculate the probability of observing more or less number of errors per page. All right. So with the binomial distribution, if we calculate then the probability of observing where x is equal to 1, then this exact probability is calculated that x is equal to 1. That is equal to 400 combination 1 times 0.05 to the power 1 times 1 minus 0.005 to the power 400 minus 1. In Excel, this is calculated as using the function binom.dist and the value of your random variable there, your n, your probability of success p, and that false means we're calculating the exact probability. Okay, it's not cumulative. Then this probability is calculated as 0.270669. All right, so you should in a way get this probability, 0.270669. Now, since we see that n is equal to 400, which is greater than 50, and p is equal to 0.005, which is less than 0.5, then we can use the Poisson distribution, or the PMF of the Poisson, to approximate the probability of the binomial random variable. So if we use then the PMF of the Poisson, then it will be calculated as e to the power minus lambda times lambda to the power x divided by x factorial. In this case, our lambda can be denoted as n times p, which is equal to 400 times 0.005, that is equal to 2. All right? Since we've met that criteria that n should be greater than 50 and p less than 0.5. And so what happens is that if we then calculate this probability there, then you will get an answer of 0.270671. So we see that these two probabilities are actually close to each other. Or the probability from the Poisson, it's almost equal to the probability from the binomial PMF. And so we see that the Poisson distribution can be seen as the limit. Why the word limit? Limit because we're looking at this case where n tends to infinity and p tends to 0. So the Poisson distribution can be used to approximate the probabilities of the binomial distribution and vice versa, provided that n is greater than 50 and p, probability of success, is less than 0.5. Right? The probability of observing some rare event should be a small probability. All right, so now this leads us to the mean and variance of a random variable x that follows a Poisson distribution. So it says here that since the binomial distribution tends to the Poisson as n tends to infinity and p tends to 0 and np tends to lambda, then the mean and variance of a binomial variable should approach those of a Poisson variable. Right? So if the binomial tends to the Poisson, then the expected value and the variance of a binomial variable should also approach those of a Poisson variable. So these limits are the expected value of a binomial random variable is in P, that will tend to lambda, and the variance of a binomial random variable n times P times 1 minus P will also tend to lambda, provided that P tends to 0 or P is very small. A proposition then says, if x has a Poisson distribution with parameter lambda, then the expected value of x is equal to the variance of x, and that is equal to lambda. And exercise 104 proves that the expected value of x is actually lambda. So exercise 104 says, let x follow a Poisson distribution with parameter lambda. Then show that the expected value of x is equal to lambda directly from the definition of expected value. So firstly, if we write the definition, the expected value of x is equal to the sum over all possible values of x times the PMF function, right? So let us start here then. The expected value of x is equal to the sum of x times the PMF function, where x now goes from 0 to infinity. That's the definition for the PM. Since under the definition of the PMF of a Poisson random variable, we noted that x will be equal to 0, 1, 2, 3, or the possible values of x is 0, 1, 2, 3, and so on, right? Okay, so now this is equal to the sum x equal to 0 to infinity of x times e to the power minus lambda times lambda to the power x divided by x factorial. All right, so now if my x is equal to 0, I'll have 0 times e to the power minus lambda times lambda to the power 0 divided by 0 factorial, plus the sum, or x equal to 1 to infinity, of x times e to the power minus lambda times lambda to the power x divided by x factorial. Isn't that true? So if we're adding from x equal to 0, meaning x equal to 1, x equal to 2, x equal to 3, 4, 5, blah, 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 we could break down the summation and calculate or substitute for each x. So I'm going to only start with x equal to 0, right? So we see then at the end we have, next line, we just have 0 plus the sum of x equal to 1 to infinity of this product x times e to the power minus lambda times lambda to the power x divided by x factorial. All right? So this is just equal to the sum of x equal to 1 to infinity of this product x times e to the power minus lambda times lambda to the power x divided by x factorial. All right. Now, what can we do? What is the next step? We said that if we have a constant, what do you do with it? You put it in front of the summation sign, right? So that is what I will do. Now, this is equal to e to the power minus lambda times the summation that x goes from 1 to infinity of x times lambda x divided by x factorial. Now we have x the numerator, then you have x factorial in the denominator. So then we will use this result that says a factorial is equal to a times a minus 1 factorial. And so this means that x factorial is equal to x times x minus 1 factorial. All right? So now this is then equal to e to the power minus lambda times sum of x equal to 1 to infinity of the product x times lambda to the power x divided by x times x minus 1 factorial, right? Since we know that x factorial is equal to x times x minus 1 factorial. Now what can we do? We see that the numerator has x and the denominator has x, so we can cancel those two there. And so at the end, you're left with e to the power minus lambda times the sum of x equal to 1 to infinity of lambda x divided by x minus 1 factorial. All right, so in the previous part of the video, we saw that we have an expression that says the sum of x equal to 0 to infinity of lambda x divided by x factorial is equal to e to the power lambda. All right. So now we see that we actually have the sum of x equal to 1 to infinity of lambda x divided by x minus 1 factorial. Can we then use this result here? Can we just directly apply it here? No, we can't. Why not? It's because if you look at the summation sign, we have x equal to 0 there, and then we have x equal to 1, right? And then the sum goes from 1 to infinity, and there the sum goes from 0 to infinity. In the numerator, we have lambda to the power x, lambda to the power x, but the denominators are not the same. They're not equal, right? So at the end, you should have an expression that says the sum of something equal to 0 to infinity of u to the power of smiley divided by smiley factorial. That is equal to e to the power u. That is the rule of the series, that it's equal to the expected value or is equal to e to the power u. Sorry. So now we see that this is not the same, right? So how can we make it the same? How can we, at the end, make use of this result here? All right, so we will multiply by a 1. Let me show you here. So we have here e to the power minus lambda times the sum where x goes from 1 to infinity of lambda to the power x divided by x minus 1 factorial times lambda divided by lambda. If I multiply by 1, it means I haven't changed anything, right? 1 times 1 is 1. 2 times 1 is 2. 3 times 1 is 3. So if I multiply by 1, I have not changed anything. Isn't that true? All right, so I can then rewrite this as e to the power minus lambda times the sum where x goes from 1 to infinity. In the numerator, I'll have the lambda to the power x minus 1. So that lambda there in the denominator, I will put it up there as lambda x minus 1 divided by x minus 1 factorial. And what are we left with? We're left with this lambda here. So this one I can take it down here, times lambda. Then we said if we have a constant, what do? We take the constant, then we put it in front of the summation sign. And so at the end, we have lambda times e to the power minus lambda times the sum of x equal to 1 to infinity of lambda to the power x minus 1 divided by x minus 1 factorial. All right, so now can we use then the result of this result here, x equal to 0 to infinity, lambda x divided by x factorial equal to e to the power lambda? Can we use it? Not yet. Why not? What is the difference? There it should be x equal to 0, not 1. All right? Then how can we rewrite it and so that we can make use of the result? We can say we have the lambda times e to the power minus lambda. Then we have the sum. X equal to 1 means that x minus 1 is equal to 0. Okay, so infinity. Then you have lambda to the power x minus 1 divided by x minus 1 factorial. And so we see that this expression here, yes, it is similar to that expression there. Then we could say this is equal to lambda times e to the power minus lambda times e to the power lambda. And so the expected value of random variable x that follows a Poisson distribution is equal to lambda. Okay, happiness? Good. So you see that it's actually not, it's just little tricks there and there, but it's really not the worst thing that could happen to you, right? Okay. In the last part of this video, part 1c, we will have a look at the probability tables of a Poisson distribution. So the probability tables can be found at the end of the textbook in a PDF called Back Matter. And so in that document, you have the appendix, which consists of the tables and also consists of answers to odd-numbered exercises, all right? So the table for Poisson distribution is given in table A2 in the appendix. So the table gives us the CDF fx for lambda equal to 0.1, 0.2, up until 20. All right? So what it calculates here is that it calculates the probability that you would have observed at most x number of successes for that period of time, where x follows a Poisson distribution with parameter lambda. All right, so we see that with the table, the first row, you're given the values of lambda, which starts from 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 8, 9, and then 1. And then you have there 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, and 20. All right, so the tables gives you lambda from 0.1 to 20, excluding 11, 12, 13, 14, and 16 to 19. All right, and then the first column of your table gives you the values of your random variable x. So that when x equal to 0 there, in the first row, essentially, it gives you the probability of x being at most 0, and the second row, probability of x being at most 1, and so on. All right, so we see that x goes from 0 to 6 in the first page, second page, then to 19, and then third page to 36. So x goes from 0 to 36. That's what the table gives you. For lambda that ends at 20. All right, so inside of the table, we have here the probabilities. These are cumulative probabilities. So the table tells you what is calculated. First row, it gives you the lambda. Column gives you the value of x. And then what we're interested in is inside the table, which is the cumulative probabilities. Cumulative probabilities, meaning you're calculating this. X is at most some particular possible value. All right, so let us have a look at an example. Suppose that x follows a Poisson distribution where lambda is equal to 4. Now, we need to calculate an expected value, the variance, and the probability of observing at most 9 successes, or the probability of observing more than 3 successes. Alright, so if x follows a Poisson distribution with parameter lambda equal to 4, then the expected value of x is equal to the variance of x, which is equal to, we literally just derived that, is equal to lambda. And so the expected value of x and the variance of x are both equal to 4. So expecting 4 number of successes, on average, there'll be 4 number of successes per period of time. And that period or space could be, for example, per page, per month, per minute, per second, per year, or annually, per hectare, per something, per a specific period of time or space. Alright, so now what is the probability that x is at most 9? So the probability of x is at most 9, this essentially, it's f of 9 where lambda is 4. So if you see me write capital F bracket 9:4, I mean that 4, it's the value of the parameter lambda, that 9 there, it's the value of x. And so what will you do? You go to your table, first row, it's a lambda. You locate your value of lambda, it's here. So any probability that you're looking for will be in this column here. And then now you will go to x equal to 9. And so you see that the probability that x is at most 9 is 0.992. Now let us then calculate the probability of x is greater than 3. The probability of x is greater than 3 is the same as 1 minus probability of x is less than equal to 3, right? And so this is equal to 1 minus f of 3 semicolon 4. So this 3 here, it's at most 3, 4 because we have lambda equal to 4. Now this is equal to 1 minus, what do? You go to where lambda is 4, and then you only look at that column there. You locate your x is 3, and so we have 1 minus 0.433. Good. So it's not or the tables of the Poisson are really not complicated. You must firstly know what lambda is. Once you know what lambda is, you go and locate that column for the corresponding lambda, and then you have a look at the value of x that you're interested in so that you can calculate your probability. And so the table only gives you this probability of x at most some particular value. It does not give you this. No. You need to, if you have a question like this, probability of x greater than 3, then this is equal to 1 minus probability of x being at most 3. And so you can use in the table to calculate the probability. And then that is the end of part 1. We did 1A, 1B, and 1C.